All right, welcome to your review video for cumulative number 8. This is the big cumulative test because the next test you take will be your final exam. So to start, questions 1 through 4 are talking about limits. Limits are going to be the bridge from pre-calculus into your calculus lives. So they are super important, which is why they've come back quite a few times on these cumulative reviews. So to start, we're talking about a limit at infinity. So limits at infinity would be talking about what's happening as x gets really big in this direction or as x gets really big in the negative direction. It's also answering the question, what's happening at the end of my graph? So limits at infinity, you're going to think about end behavior. And so we want to consider how is my top function compared with my bottom function. And both of these have a degree of 1. So this function would be what we call even in heaviness. They are racing at the same speed, but this one is going 9 times and this one is going 5 times. So the limit is 9/5. This next one, the limit as x goes to negative infinity. So again, in that case, we're just going to the left as x gets really big in the negative direction. And again, we're comparing the top to the bottom. And this, I notice I have a quadratic on the top and a linear on the bottom, which means that this would be what I call top heavy. And so if you remember from top heavy, end behavior would be some sort of a slant asymptote. So when we're talking about the limit, we've got to figure out which way is my slant going. Is it going like this? Is it going like this? Maybe it's some sort of a parabola in shape. And then from there, I can answer this limit at infinity based off of my up, up, down, down, up, down, down, up with even and odd polynomials. So you can do the full long division if you want to, but also you can just tell yourself, okay, this is a quadratic, this is a linear. My first step in doing the division would be to say x squared divided by 20x, which leaves me with 1/20th x. I don't really care what the rest of this is. I just know that this is going to be my slope. So if I were to plot this, it's going to have a slope like this. So as x goes to negative infinity, my y values are going also down to negative infinity. All right, limit as x goes to 5. Sorry, I'm a little bit under the weather if you can hear that in my voice. But the limit as x goes to 5, first method for finding a limit at a point is to plug in that value. So I'm going to plug in 5 minus 5 over 25 minus 25, and I get 0 over 0, which means I need to keep going. Well, a way to keep going would be to use algebra. So this is going to be a difference of squares, x plus 5, x minus 5. Now these things cancel. So I have the limit as x goes to 5 of 1 over x plus 5. Brand new limit problem, plug in 5, I get 1/10. This one, the limit as x goes to 81. Again, first method is to plug in the value, to substitute in your 81. And I get 0 over 0, which means I need to keep going. This one I could multiply by a conjugate. So the square root of x minus 9, I'm going to need to multiply by the square root of x plus 9. But if I do that in the numerator, I also need to do that in the denominator. But remember that you're only going to multiply the top, or the one that needed the conjugate, to get rid of the square root. So this is going to become x minus 81. And I don't want to multiply out the bottom because you'll notice my goal was to get something to cancel. And if I don't multiply out the bottom, then I can see that those cancel. 1 over the square root of x plus 9. This is the limit as x goes to 81. Brand new limit problem. Now when I plug in 81, I get 1 over 18. All right, it is 2019 and you invest $1,000 into an account that pays 1.4 monthly interest. How much is your account worth in 2025? So we're going to use our amount is equal to the principal times 1 plus 0.014. Monthly would be 12 times per year. And I want to know what's going on in 2025. Well, in 2025, that's going to be 6 years away from 2019. So using your calculator, go very carefully with order of operations, we should get that our balance is $1,087.58. Part B then says, in what year? So that means I'm looking for this time, t. You should notice that t is up in the exponent, which means that inevitably I'm going to need to use a logarithm at some point. So 5,200 equals 1,001 plus 0.014 over 12 to the 12t. First thing I'm going to do is divide by 1,000. So this will be 5.2 equals, I'm going to grab my calculator real quick. Where's my calculator? There it is. All right. So using my calculator, I'm going to do this 1 plus 0.014 divided by 12. So I get 1.0011. 1.0011. And I think there's a bunch of sixes. Yeah. 6, 6. That'll be good to the 12t. So now again, my variable is up in the exponent. To get something down, I'm going to take a logarithm. You could do a log with this decimal base. I'm just going to choose natural log because I know my calculator has that button. That will allow me to swing this 12t down in front. And now my goal is to isolate that t. So I'm going to take the natural log of 5.2, divide it by 12, divide it by the natural log of 1.001166. You should get about 116. I guess I can actually do it. I know the final answer is supposed to be. So we've got natural log 5.2. We're going to divide that by 12. Then we're going to divide that by the natural log of, well, I'm actually going to go up and grab my answer so I get as many decimals as possible. So you get t is 117. So it asks about in what year. So I was in 2019. I'm going to add this 117, but if you look, it's actually kind of close to 118. So I would say 2137, okay, just with a little bit of rounding. If you said 2136, we probably would still accept that answer, but just consider what's applicable for your situation. All right, solve each equation. So the first two, 6 and 7, looks like I have variables up in the exponents, so I'm going to need a logarithm. Numbers 8 and 9 looks like I have logarithms, which means I'm going to need exponents. So I'm going to start by taking, you could use a log base 6 if you have a fancy calculator. I'm going to choose just the natural log because I know that I have that button on my calculator. So that allows me to swing this 5x plus 1 down. So that means that 5x plus 1 equals the natural log of 9 divided by the natural log of 6. X then will equal the natural log of 9 divided by the natural log of 6 minus 1, all divided by 5. That would be your exact answer, which ends up being about 0.045 if you round to the nearest hundredth. This one, before I can isolate, or before I can get to my exponent up here with the logarithm, I got to get rid of this 3. So 7 to the 4x minus 7 is going to equal 13 because I'm going to divide out. Again, I could use a log base 7 if I've got a fancy calculator, but I'm going to choose natural log because I know that my calculator will have that button. That allows me to swing the 4x minus 7 down in front. That means that 4x minus 7 is equal to the natural log of 13 divided by the natural log of 7. X will equal the natural log of 13 divided by the natural log of 7 plus 7, all divided by 4, which, if you use your calculator, we should end up with 2.080. You could check those answers by plugging back in and make sure that 6 to the 5 times 0.045 plus 1 is, in fact, 9. Now, the reason I didn't rewrite in bases is that 6 and 9, while they're related with 3, kind of, they won't both be written in base 3. And then 7 and 13, there's no way that you're going to get those to match in terms of their bases for exponentials. All right, logarithms. Before I can use an exponential to undo a logarithm, I need to have a single logarithm. So I'm going to use my properties of logs. This addition can turn into multiplication. So now, to get rid of this log base 8, I can either do this little recycle thing, or I could use an 8 on both sides. Either way, the log is going to cancel out. I'm going to have x squared plus 12x is equal to 8 squared. So that means that x squared plus 12x minus 64 is equal to 0. Thinking about factoring, that's going to be positive 16 and minus 4. So x equals negative 16 and x equals 4. But because the logarithmic function has a domain restriction, I have to go back and check. Plugging in 4, I would get 4 there, that's fine. 4 plus 12 is 16, that's fine. But plugging in negative 16, the natural log of negative 16, or even the natural log of negative 4, that one's not going to work. So it's just x equals 4. Number 9, same approach. I'm going to use some properties of logs to condense first. So this subtraction sign will turn into division. So now to get rid of this natural log, I can think of it having a base e here, and I can do the little wraparound, or I can e both sides. Either way, e and natural log are going to cancel out because they are inverses of one another. This becomes e to the third. And then I'm going to choose to multiply both sides here by x plus 1. So 5 equals e to the third times x plus e to the third, okay, because that's e to the third times x plus 1. So I'm going to subtract my e to the third. 5 minus e to the third equals e to the third x. And then I'm ultimately going to divide by this e to the third. Oop, that x should still be there. So when you do that in your calculator, you will get negative 0.751 if you want a decimal answer. All right, that was mostly Unit 10 there, all those exponentials and logarithms. Now we're going to jump back to Unit 9, thinking about rational functions. It says to analyze the rational function, basically check for all the things. So first thing you want to do is notice that you have a cubic over a quadratic, and you're going to start by factoring so that we can read the domain. So this bottom part is going to factor pretty nicely, x minus 9, x plus 3. This top one, I'm going to try, because I have 4 terms and a cubic, to factor by grouping. I'm going to do this off to the side. So I'm going to have x squared times x plus 6 minus 9 times x plus 6, which means I really get x squared minus 9, x plus 6. So this will be x plus 3, x minus 3, and x plus 6. So thinking about my domain I read before I cancel anything out. So negative infinity to negative 3 to 9, 9 to infinity. So I got that part done. Now I can cancel things from top to bottom. So x plus 3, x plus 3. So that means that there is a hole at negative 3. The way that I get the y value is by plugging negative 3 into what's remaining. So when you plug negative 3 into there, you're going to end up with 3 halves. The thing that was left in the bottom creates my vertical asymptote. So x equals 9 is going to be a problem spot that I can't remove. Then I got to think about my end behavior asymptote. So if I start back at the beginning, I notice that this function is top heavy. So I'm going to have some sort of a slant, which means there is no horizontal. And my slant would come from doing the division. So I could start here and do long division on this whole thing. But it's easier if you use the long division, or rather synthetic division, on this part that you have here. So what I have going on is x squared minus 3x minus 18 being divided by x minus 9. So I can throw a 9 in the synthetic box, 1, negative 3, negative 18, and do some synthetic division. That's going to make things a lot nicer. Ooh, I just realized it should be plus 3. My apologies. So it'll be 12. 9 times 12 is 108. Mental math. So that's going to end up being 90, but I don't actually care about the remainder. This is the part that creates my slant asymptote, x plus 12, which makes sense because x to the third over x squared should get me a positive x for my linear slant asymptote. All right, so we're cruising. X-intercepts by definition is what happens when you set the whole thing equal to 0, right? When y is 0. So I have x minus 3 and x plus 6 over x minus 9. That was my simplified function. So thinking about what makes that 0, I really just care about where the top is 0. So that's going to be at 3, 0 and negative 6, 0. And then my y-intercept is going to be what happens when I plug in 0 for x. So 0 for x, 0 for x, 0 for x, 0 for x, 0 for x. I get negative 54 divided by negative 27, which will be 2. All right, so that one went pretty fast, but there's a really good video in Unit 9, it's 9.7, that does a summary of all of those things. If you need a reminder on any one of those pieces, you could go back to 9.7. All right, we'll pick up with number 11 in the next video.